Hello, everybody. In this chapter, we're going to discuss what's referred to as chemical thermodynamics. Your textbook defines this as entropy, free energy, and equilibrium. So we're going to introduce some of these concepts and definitions. And in this first section, we'll talk about what a spontaneous process is. So first, let's define the first law of thermodynamics, which states that energy cannot be created or destroyed. Another way of saying that is that energy is conserved. The total energy of the universe is constant. That's also another concept that ties into this. But we can convert energy from one form to another. And energy can also be transferred from a system to the surroundings, or the other way around, from the surroundings to the system. So we'll define a little more what that is in a later section. You may recall this term here, enthalpy, which I have the definition here as the heat absorbed by a system during a constant pressure process. And we'll elaborate again on what this constant pressure refers to, but if you're familiar with the enthalpy term or the change in enthalpy, delta H, you might recall these terms defined in earlier chapters. Exothermic is where we have a negative delta H, where the system releases heat to the surroundings. And an example of a reaction that would have a negative delta H is a combustion reaction. If you ever used a barbecue grill, the gas combusts and produces heat. So you can actually feel the energy being released, the heat being released. An endothermic process is where we would have a positive delta H, positive change in enthalpy, where the system would absorb heat from the surroundings. And an example of this could be ice melting. So again, a spontaneous process here, by definition, is a process that will proceed without any outside intervention. So really that means without adding any energy, the process will just go by itself. So we should also note that processes that are spontaneous in one direction are non-spontaneous in the reverse. So if the forward direction is spontaneous at that same temperature and other conditions, the exact process would be non-spontaneous in the reverse. So we can look at a process here that is reversible, the freezing and melting of ice or water. So what we see here is frozen water, ice on the side, and a spontaneous process occurs below 0 degrees Celsius. Ice will go from liquid over here in liquid phase to over here in solid phase. So at below 0 degrees Celsius, what we're stating as the reverse process here is spontaneous. But then if we're above 0 degrees Celsius, so room temperature, for example, is around 25 C or so, the forward process here, going from solid to liquid water, would occur. So again, under the same conditions at a certain temperature, so 0 C, we would see spontaneous in one direction, but non-spontaneous in the reverse. At 0 Celsius, water does not start to melt. Or ice in this case would not start to melt. So let's look at another example here of a process that, say we have gas here in vessel A, and it's charged at 1 atmosphere. And then we have what's referred to in the middle here, this closed stopcock. So there's a valve here that's closed and no gas is able to get to this evacuated flask, which has 0 pressure reading. So when we open that, what we'll see is a spontaneous process where the gas molecules will move from vessel A to vessel B. And then it looks like about equal pressure will equilibrate. Once we open that stopcock, the gas will expand, and we see that happen spontaneously. Now, what's noted here is that the gas molecules with the valve open, the stopcock open, will not spontaneously move back into just one side, one vessel A here. So this is not a reversible process, not a spontaneous process in the reverse. So even if we change temperature, other conditions, without physically pushing all those gas molecules back, it would not be spontaneous in this reverse direction. So let's take a look down here and see if we can identify with this information what a spontaneous or non-spontaneous process could be. So in example A here, we're asked if the decay of a piece of wood buried in soil would be spontaneous, so or not spontaneous. So we can think about just the natural process of organic materials. Decay, we know, is just something that occurs spontaneously. If you ever left a piece of fruit out on the counter, maybe an apple that you cut, you can see it change color. And then if you kept it out for a couple days, you would see it decay. So this is a spontaneous process. We'll list an S there. In example B now, we're asked if the formation of sodium, so solid metal, sodium metal, and chlorine gas, Cl2 gas, in a vigorously stirred aqueous solution of salt water, right? Sodium chloride here. So if we could think of this in the reverse, if we stirred an aqueous solution vigorously of salt water, would we make metal and chlorine gas? Well, thankfully, no. This would be a non-spontaneous process, no matter how hard you stirred that, how vigorously you stirred that. I have never been able to make chlorine gas by stirring salt water. So we'll put an NS for that one. And then let's take a look at C here, the ionization of hydrogen chloride, so HCl gas, right? When we dissolve this in H2O, this is hydrochloric acid, right? So this, we know, we should write it as ionized here. Hydrochloric acid always ionizes 100% in solution because it's a strong acid. So this would be, once again, a spontaneous process. So we'll continue in the next section with more about thermodynamics.